particle has initial velocity u is 3I minus 5j meters per second, and a final velocity of v equals 2I plus j after 2 seconds. So what I'm going to do, I'm going to take this information generally through the question and take the acceleration to be constant, because this only works if you have a constant acceleration here. And because we're given our initial velocity, that's 3I minus 5j meters per second. We have v is 2I plus j meters per second. That is after 2 seconds. We want the total displacement of the particle in those 2 seconds, so we want to find our displacement vector, which I call x for now. Underlining them because I want to make sure we know it's a vector. So here we can use the Subat equation. We've got S, U, V, and T. So S equals a half of U plus V times T. So my position vector is going to be a half of 3I minus 5j plus 2I plus j meters. And this was seconds and meters here. Which in this case is going to be a half of, that times 2, because of time as well. So a half and the 2 cancel out. So that's not going to be needed. We've got 3I plus 2I, which is 5I. And we have negative 5I plus j, which is minus 4j. So our position, our total displacement is 5I minus 4j meters. To find the acceleration undergone by the particle during this time, so again we're going to use those Subat equations, S, U, V, and T. Well, U, V, and T were given, so let's write that down again on this slide. So U is 3I minus 5j. I'm not going to write the units this time. V is 2I plus j. And T is 2. This time we want to find the acceleration undergone. So the acceleration is what we're trying to find. So we can use V equals U plus a t. So 2I plus j equals 3I minus 5j plus at. So plus 2a. So if we take away 3 i's from both sides, we've got negative I. Add 5 j's plus 6j equals 2 times our acceleration. So our acceleration is negative a half I plus 3j meters per second squared. If the final position is 3I minus 5j, and we know from earlier on that our displacement during those 2 seconds is 5I minus 4j. Our displacement was 5I minus 4j. Our initial position vector is going to be our final position, take away our displacement. So that's 3I minus 5j. And we're taking away 5I minus 4j. Careful of the double negative there. So we have 3 minus 5 i's, and then we have negative 5 plus 4 j's, which is negative 2 i's, take away 1 j. That will be our initial position. The acceleration remains constant for this, so our acceleration is going to stay at negative a half I plus 3j. We want to find the speed and direction of the motion at the end of the 4 seconds. At the end of 4 seconds. So 4 seconds is key here because we've been using 2 seconds so far. Okay? Which means this is only applicable to the first 2 seconds. That is our final velocity after 2 seconds. So we're given our value of u still. Our value of u doesn't change. 3I minus 5j. We don't know what v is. We don't know what our displacement is. But we know our time is 4 seconds. That's all the information we're given. So, let's do part 1 then. The speed, we want to find the speed and direction of motion at the end of 4 seconds. So we're trying to find v. So in order to do that, we need to use v equals u plus at. So our v is going to equal 3I minus 5j plus negative a half I plus 3j times time, which is 4. So we have 3I minus 5j minus 2I plus 12j, which is I plus 7j. That's our final velocity. And if we're to get the direction, the actual speed and direction, the speed is going to be the square root of 1 squared plus 7 squared, because the speed is a scalar quantity, not a vector quantity, which is the square root of 50, which is 5 root 2 meters per second. And our direction of motion, well, if we're going I plus 7j, so that's I is 1 to the right, 7, well, 1 east, and 7 is, 7j is 7 north. So if what we'd like to do is find the bearing, really, of that direction. This is north. We need this angle here, which is this angle here, because of alternate angles. So theta is going to equal the inverse tan of 1 over 7. And make sure you write the answer to that too, using 3 digits. That's the angle from north. And part 2, which I'll do in red, the displacement and position vector after those 4 seconds. So this time we want the displacement. So we've got S, U, A, and T. So S equals UT plus half AT squared. Which is 4 lots of 3I minus 5j plus a half times t squared, which is 4 squared, times a, which is negative a half I plus 3j. So that's going to be 12I minus 20j, 4 fours are 16, half of that is 8. So 8 times negative half is negative 4 i's. And then 8 times 3 is 24, so it's 24 j's. Which overall is 8 i's plus 4 j's. That would be our displacement. So the position vector is going to be based on our initial position. Our initial position was negative 2i take away j. So our new position, evaluated when t equals 4, is going to be our initial position. Let me just double check it. -2, -1. -2i minus j, add our displacement, which is going to be 6i plus 3j. That's our new position vector. If we want the distance between the initial position and the position after 4 seconds, then for the third part, which I'll do in black, the distance between the initial position and the position after 4 seconds, that is all to do with our displacement. Our displacement from our initial position was 8i plus 4j. And our distance between them then, our distance is the magnitude of our displacement, which is the square root of 8 squared plus 4 squared, which is the square root of 64 plus 16, which is the square root of 80, which is 4 root 5 meters. Let's not forget units for these. So our position vector would have been in meters, and our speed meters per second. Good. And this would be a bearing in degrees, making sure that we use degrees, not radians.